started in soon. Okay. And let's talk about what we're going to talk about today is another technique for finding volume of solids of revolution. It is no longer a tested topic in BC calculus. So it won't be on my test and it won't be on the AP exam. However, some of you are going to skip Cal 2 and go on to Cal 3. And it's taught in every Cal 2 class in college. So today's kind of a weird day that I'm throwing in a topic that it's not I say it's not on the BC test. There are problems that are much easier if you know this topic. So there are problems that you can do on the BC, kind of like L'Hopital's rule. This could help you on a problem. But every problem on the BC exam can be solved using discs and washers. Y'all remember that problem where we had to split it into two parts? Which tells you would do one part. So that's what we're going to be learning today. But I do want you to know we have two topics that I'm going to do this with that they have taken out of the BC curriculum. They used to be in BC, but they've taken out of the BC curriculum. But they're in every Cal 2 class in college, and I debated a long time on what to do about that, because part of it's like, oh, it's not a test, we're wasting our time, but part of it's that a lot of you are going to be engineers and gone to Cal 3, and you will need to know it. Those of you who are not going on, if it confuses you after tonight's homework, you can just do everything with discs and washers, and that's fine. So it's up to you, kind of take that as you will. On my exam, I'm going to pull AP questions. Well, there are no AP questions that you can't do with discs and washers. There are problems in Cal 2 that you can't do with discs and washers. So just throwing that out there. This is kind of a weird day where we're doing a topic that's not on the BC test.
How far does Newton get into all of this?
When did this stop?
What?
I don't know so far he went.
Because how much of this was his and how much of this was everybody after him?
I mean, a lot of it was a continuation. So I don't know how much he did volumes. So anyway, the first one, did everyone agree? It's actually a disk problem, a rare disk problem. Do we agree? It's not even a washer. No. A cube root. So if I graph the whole thing, I would get something that looks like that, right? But I am using the region that is trapped here. Everyone agree? Because I'm rotating around the x-axis, there is no gap between the region and the x-axis, so this is a rare disk problem with lattice in the rare event that they come up. So how do I find a volume? Do I?
It would be from 0 to 8.
0 to 8.
Of the top, which is the cube root of x, minus the bottom, which is nothing. So
okay, so we're doing the radius of the disk, right? So I'm rotating this around the x-axis, so I get this shape here, and I get a disk there. The radius of that disk is the cube root of x. So it's the cube root of x squared. Pi r squared. Remember, the volume of a disk is pi r squared. So you're multiplying pi times the radius squared. And 0 to 8. Any questions about that? Good? When we're rotating around the x-axis or any horizontal line, it always ended up being dx, right? If we rotated it around any vertical line, it always ended up being dy. So let's look at the next one. It says, oh, don't do it, right? Why is it so hard? Find the volume of the solid obtained by rotating around the y-axis, the region bound by this. I could almost stop there, and you could probably tell me why it's so hard.
Infinities.
Okay, that's the key. If I'm rotating around the y-axis, isn't this a dy problem? Solve that for x. Good luck, right? Do you see why it's next to impossible? Because solving that equation for x be awful, maybe impossible. Because of that, this is something that we couldn't do with discipline washers. So this is what we're going to learn how to do today using another method. And I wanted to show you this problem to show you why in Calc 2 there is another method. Because at some level you're going, well, why? If discipline washers always work, why can't I use them? They don't always work. They always work in BC calculus, but they don't always work. So that's why this method exists. And so that's what we're going to learn today. And it's called cylindrical shells. If we can find the volume of a cross-section, it doesn't matter what shape of a cross-section we make, correct? We did squares, we did, what else have we done? Triangles, we've done semicircles, but it just turned out that washers and discs were a big portion of those cross-sections. Well, what I can do is if I have something rotating around, instead of slicing it this way and making a disc out of it, I can pull off a layer of it, kind of like an onion, like how you can peel a layer of an onion off. We can push back or something. No, I'm just going to do that. But we can take layers of that off and get cylinders. Would everyone agree if I'm rotating around an axis, a horizontal or vertical axis, I could make little cylinders? Well, I want the little volume of this guy, this cylindrical shape. Well, if I open it up and make it into a prism, a rectangular prism, everyone see what I'm talking about there? If I open it up and make it into a rectangular prism, the width of that would be the circumference. Everyone agree? 2 pi times the radius would give you the circumference of the shell, of the cylindrical shell. And then you would multiply that by the height. And you'd add all of those cylinders up, or add all of the layers of the onions up. And so that's called volume by cylindrical shells. Now the formula I have up here is really too simplistic. If you'll read, it says, and this is what a lot of textbooks write the formula as. I don't like it because we have to modify it. So I'll show you what we will kind of rewrite it as. But this formula is only if you're rotating around the y-axis. Now I want to point something out. In discs and washers, when we rotate around y, what do we integrate with respect to? dy. But in this case, if we rotate around the y-axis, what do we integrate with respect to? You see why shells are important. That last problem, we now can keep it at dx. And so that's why shells are nice. That's kind of the big thing with shells is the dx and dy are opposite. If you rotate around the y-axis, it's dx. If you rotate around the x-axis, it's dy. And so you do the circumference of the shell, which will change with the pieces of the function. Now this has it rotating around the y-axis, in which case the circumference, 2 pi r is the circumference, right? So that little x is actually the radius. The radius would always just be the x value of the function. Does everyone agree? Wherever you are on the function, the radius would be the x value of the function. Of course, that will change if we're dy. So instead of writing this formula this way all the time, I'm going to write the integral from a to b. I'm going to go ahead and factor the 2 pi out. Why not, right? Of the radius times the height. And dy or dx, depending on which way we're going. So it's the radius of the shell times the height of the shell. Again, if we were rotating around the y-axis, which is that's the common time we would want shells, so we don't have to solve for x. And that's why textbooks a lot of times simplify it down to only teaching you that, because a lot of times you just get discs or washers if it weren't. The dx is the little width of that shell, and so you're adding all those widths of the shells up. And f of x is the height. So the height of the curve, when you agree that would be the height of the shell. And so that's where the f of x comes into play. So I have an example here. I got this picture online. I didn't really draw it. I know y'all thought I did.
Totally with the computer netting.
Yeah, yeah. So it's a hidden skill I had you didn't know about.
Oh, and the shading for this too.
Thanks. My artwork. How great I am at drawing pictures.
It's great.
Find the volume of the solid found by rotating that region about the y-axis that's bounded by 2x squared minus x cubed and the x-axis. So if you were to graph that, of course, there's more to the graph. That's the part bounded by the x-axis. And I want to rotate that around the y-axis. I put a graphic here on this one. Next one I'll do without a graphic, so you can. We're kind of easing into shells. Again, if it's around the x or y axis, it's not too terrible. Just like this in washers, you start moving on it to a different axis, then we'll have to think a little harder. Okay, so I know that I need the integral, the radius times the height. And since I'm rotating around the y-axis, it will be dx, because the little width of the shells will be changing x. Any questions so far? What is the radius of that shell? X. It's wherever this, right, the shells get bigger or smaller, right, the radius will be the width from the y-axis to the which is the x value. Again, if we are rotating around the y-axis, the radius will always be x. So you saw in that formula where they just called it x. But if we're not rotating around the y-axis, that would change some things. The height of the shell will be the height of the curve. Questions about that? So, 2x squared minus x cubed. We are integrating dx, so we will go from 0, it looks like they gave us the intersection. If we didn't know that intersection, you would find when that equals 0, it is factorable, so 0 and 2, and that's where they get the 2. Any questions about that? This one is one that's set up where it could be on a non-calculator portion of an exam, and you could have to integrate. Can I integrate that by hand? What would you do first? Distribute the x, anti-differentiate. Any questions about that? I'm going to go on if don't mind, but just wanted, if there are any integration questions. It could do that though. Any questions? Okay. Find the volume of the solid obtained by rotating that figure around the y-axis. So the region bounded by x minus 1 times x minus 3 squared and the x-axis around the y-axis. Sure. You forgot your 2, I believe. Yeah. Find the volume of the solid obtained by rotating that region around the y-axis. So this is another y-axis. And you may ask yourself, why I am going to do an example that's not y-axis, but why am I showing you so many y-axis problems? That's where you could use it on the BC exam. Is a problem that's a very difficult discs and washers problem. You could turn it into a shells problem and use dy or use dx to make it a little easier on you. AB teachers also teach cylindrical shells because of that reason. I never have because I feel like in AB it's more likely to confuse them than to help them. So I just stick with one way in AB, but like I said, I felt like I couldn't leave y'all hanging in your Cal 2 experience without exposing you to cylindrical shells. So far, how's it feel? Okay. Did that one problem?
Yeah.
Yes. I saw that. I was surprised because that was on an AB exam. Again, some AB teachers teach it, so I guess that's why. But on the AB and BC exam, there are none that you are required to use shells. There are some that are easier that way. That one's easier though, wasn't it? Because did you have to break it up? Or
I didn't know that.
was it harder with this? Was it hard with this?
I don't remember.
I thought it was hard. You couldn't do it. So that's where cylindrical shells, even though theoretically it should be able to be done, maybe. I might have to focus on it. Oh, not on the exam. Piston washers. Well, I mean, there's like a bell ringer. I'm going to show you it with shells. But you would never want to do it with shells. No. No, you can always use whatever you want. And if shell is easier, just like L'Hopital's rule in AB. L'Hopital's rule is not an AB topic, but they will never count on it. So, cylindrical shells, not a BC topic or an AB topic. But it can simplify some rotation problems. So if you find that cylindrical shells will be easier and you're good at them, by all means, use them. So this is kind of a chapter that can help you, but it's not something you have to do for this sketch. Find the volume of this solid. So let's look, and I have a picture, but I have not drawn this cylinder on this one on purpose because I wanted you to see how to draw the cylinder, okay? So we are rotating this around, and so we will make cylinders. Does everyone kind of see how that works? Out of, when we rotate it, each piece of we'll layer it off in cylindrical shapes. Alright, so on these cylinders, remember I need 2 pi times the integral of the radius times the height of the cylinder. Since I'm rotating around y, it's going to be a dx. For the region, you always do the endpoints of the region. So what are the endpoints of this region? 1 to 3. It is tempting to want to go from 0 to 3, but you would end up picking up that curve that goes below the x-axis, which you don't want to do. You only want that 0 or 1 to 3. The radius is x. Does everyone see how I get that? The height, what is the height of all these cylinders? The height of the curve. Now you notice it goes up and down. If you were to have to do this with this in washers, you would have to split this into 2 pieces. Wait, I mean, you couldn't solve, but it would be pretty nasty, right? So we get to just use the height, which is x minus 1 times x minus 3 squared. The textbook that I got this out of also integrated this by hand. I'm not going to waste our time doing that. You would have to distribute a bunch of things. So you have to FOIL x minus 3, then multiply by x minus 1, then multiply by x, and then it wouldn't be difficult. The difficulty in here is the algebra. Any questions about the setup of this one? It is, you're right. Nope, you're right. I think I said it right, but you're right, I did not write it down. I wrote it down right. Now, endpoints should not change unless you're doing use substitution. Okay, I want to show you a nasty one. worse, and we could have had to do everything with shells, right? And so this is a shells problem that doesn't work out quite as nice as the others. First of all, what am I rotating around? The x-axis. So instead of dx, this would be a dy. So I want to look at what this would look like with a nastier problem. So I know that I would be 2 pi times the integral. Remember, the reason it's 2 pi r times h, the cylinder, the area of that prism pulled out on the cylinder. 2 pi r times h, and this time it would be dy. Which means I'm going to solve the equation for y, right? Not too difficult. That part's not too difficult. So I get x equals 1 cubed. And so I have this cylinder going around this way. Let me see that cylinder. The height or the radius of the cylinder is not too bad. Everyone agree it's just y? It's the height of this curve, which would be the y value, and since we are getting dy, that's easy enough. The height would be, or the radius would be y. The radius of the cylinder would be y. Questions so far? However, the height of this cylinder would be a little trickier because this cylinder is inside this parabola, right? So it's the distance from 8 to here. Everyone agree? Questions about that? So it would be 8 minus y cubed. That would be the height of the cylinder. So I get 2 pi times the integral of y times 8 minus y cubed. So it didn't end up just being the curve. It ended up being 8 minus the curve. Why is that? Kind of like discs and washers. You know how when you see a gap? You see how we have this gap over here on the outside? That's what's causing us to have to do that subtraction. That way. We are integrating dy. Any questions so far? Here's the textbook work there. The region would be 0 to 2. Does everyone know why it would be 0 to 2 instead of 0 to 8? Because we are integrating the region on the y-axis. Remember our region, which I kind of lost that in this picture. This was the region here. And so that's y is from 0 to 2. Any questions about that? So they, again, this textbook that I was giving these problems out of, so I can get a few pictures, they integrated everything by hand. So you can see that integration they did there by multiplying things out. Any questions? Questions? No? Is this making sense? Okay. Tomorrow will be a work day. I did mix in problems with shells and disc and washers because I don't want you to forget or replace your disc and washer knowledge with shell knowledge. So I picked some problems of both. There are some that tell you to do it with cylindrical shells and tell you to do it with disc and washers. And then others you get to choose. So choose wisely. So this is your homework. It is due Monday. Tomorrow is a work day. Those of you who have test corrections to do this at home. That way you can just ask questions tomorrow, be done with it, and then use tomorrow to work on test corrections. If you have those to ask questions on. This is due Monday.
How long is this going to take? Because, I don't know, it's kind of short.
It is volume, so those always took you a little longer to